Hi, I'm Phil Ambrosini. I work here at the college at the Learning Center. I tutor mathematics. My background in statistics is that I did my graduate work at Florida State University. Here I am, a northerner, having come all the way down to Tallahassee to do my graduate work. I've been a practicing statistician. I was a practicing statistician before retirement for 40 plus years. I did most of my work in the area of direct marketing and database marketing, but I've also touched other areas. It's been my experience over the years that when it comes to hypothesis testing, the probability of committing a type 2 error, that beta error, is really given short shrift. For those of you of the appropriate age, I want you to think of Rodney Dangerfield, the comedian, the googly-eyed guy who always was tugging at his tie saying, I get no respect. Well, neither does the type 2 error. So we're going to try to give it some respect in this presentation. When it comes to testing hypotheses, most elementary stat texts focus on controlling the probability of committing a type 1 error, to the exclusion, almost, of not worrying about the probability of committing a type 2 error. Now, what I want to do in this particular presentation is take a look at setting up an hypothesis test in which we are concerned with controlling both types of error, the probability of committing both types of error. So just to refresh everyone's memory, let's take a look at this slide. If the null hypothesis is true and we reject it, we've made a mistake. We've committed what's called a type 1 error. Whereas if the null hypothesis is true and we fail to reject it, that indeed is a correct decision. If the null hypothesis is false and we reject it, again, that's a correct decision. However, if the null hypothesis is false and we fail to reject it, we've committed a type 2 error. We're going to let alpha be the probability of committing a type 1 error and beta be the probability of committing a type 2 error. The scenario I want to take a look at is borrowed from the world of direct marketing. Let us assume that we have a target population of prospects that is 10 million in size. And we have budget to do a mailing of 1.5 million, which we're going to randomly select from the target population. Now, we have a control package, a control promotional package that we've been using over time, and it generates a 3% pull. The term pull in the direct marketing industry refers to response rate. So this control has demonstrated a 3% response rate over time. We've come up with a new promotional package which is felt will generate a 3.5% pull. And we've gotten this result by randomly selecting 2,500 prospects from our target population and actually mailing them the new promotional package. And we find that the response rate is 3.5%. Now, that new promotional package may have taken what already existed and perhaps come up with new descriptions for the product or products if it's a catalog. May have actually introduced a sweepstakes, which typically does increase response rate. Whatever combination of elements we've used has increased the response rate to 3.5%, at least based on our testing. Now, there's always a cost involved in generating an increase in the response rate. The cost of mailing the control package is $2.80 per piece. The new promotional package has a cost of $3.40 per piece. Typically, the revenue per sale is $150. Now, that could come from selling an upscale product, or perhaps it's a catalog in which the average sales turn out to be about $150. Okay, it would seem reasonable that what we would want to do in this situation is test the null hypothesis that the population response rate or population pull is 3% versus the alternative that it is greater than 3%. This is a one-sided test, and specifically it is a right-sided test. Okay. Now, let's take a look at the possible decisions that can be made in this scenario. If we commit a type 1 error, that means that we have rejected the null hypothesis that the population pull is 3%, when that is actually true. Now, if you reject the null hypothesis in favor of the alternative, okay, then the 1.5 million randomly selected prospects would be presented with the new promotional package. I mean, that's our decision. We're rejecting the null hypothesis. Now, the revenue associated with this decision, you've got those 1.5 million names, okay? Because the null hypothesis is actually true, the new promotional package is not going to have any effect, so the response rate is going to be 3%. And, of course, it's $150 revenue per item or combination of items sold. Therefore, the arithmetic says that the revenue turns out to be $6,750,000. What's the cost? Well, 1.5 million packages. Since you've used the new promotional package, that's $3.40 per package. Therefore, you have a cost of $5,100,000. If you subtract the 5.1 from the 6.75, you have a profit of $1,650,000 associated with the type 1 error. Now, I am going to summarize all of this in a table after we go through each scenario. So let us move to the next one. Suppose we fail to reject the null hypothesis, 3% pull, when it is actually true. Now, we've made a correct decision here. So if we fail to reject the null hypothesis, we're going to randomly select the 1.5 million prospects, and we're going to present them with the control package. All right, what's our revenue here? Well, 1.5 million names, 3% pull, $150 revenue per item sold or combination of items sold. There's that $6,750,000 once again. However, the cost, because we've used the control package, the cost is reduced. It's 1.5 million times $2.80 per piece, and therefore the cost is $4,200,000, leaving you with a profit of $2,550,000. Okay, the next scenario, what happens if we commit a type 2 error? All right, that means that we fail to reject the null hypothesis when it is actually false. So we're going to go with the existing control package. Okay. The revenue then would once again be $6,750,000. The cost, $4,200,000, and the profit, $2,550,000. It's exactly what we've seen in the previous scenario. Okay. Suppose we reject the null hypothesis when it is actually false. In other words, now we've done the right thing. It's a correct decision. If you reject the null hypothesis in favor of the alternative, which is going to be represented by a 3.5% response rate, then we're going to randomly select 1.5 million prospects, and we're going to present them with the new promotional package. The revenue there is 1.5 million times, now 3.5%, because we have enough evidence to believe that the new promotional package has increased the response rate. So 1.5 million times 3.5% times $150, that is a revenue of $7,875,000. Our cost, since we used the new promotional package, is $3.40 per piece. We've mailed 1,500,000 individuals. Therefore, the cost is $5,100,000, and leaving you with a profit of $2,775,000. As promised, a summarization of these profits based on the possible decisions that can be made. So if we commit a type 1 error, okay, null hypothesis being true and we reject it, we make a profit of $1,650,000. If we don't make a mistake and we fail to reject the null hypothesis when it is true, okay, we make a profit of $2,550,000. In other words, if the null hypothesis is true and we make the correct decision, we make an additional $900,000. Or another way to look at it, if you commit a type 1 error, you're leaving $900,000 on the table. What if the null hypothesis is false? Well, if the null hypothesis is false and you reject it, you're making a profit of $2,775,000. If you fail to reject the null hypothesis when it's false, you've committed a type 2 error, and that has a profit associated with it of $2,550,000. In other words, if you commit the type 2 error when the null hypothesis is false, you are leaving $225,000 on the table. Now, in this particular scenario, obviously it is worse to commit a type 1 error. However, committing a type 2 error is causing you to lose $225,000, and that's certainly nothing to sneeze at. All right, so let's take a look at the actual test of the null hypothesis of the 3% pull versus the alternative of a population pull that's greater than 3%. And we're going to do this at a level of significance alpha, which we're going to set at 0.05. Typically, in the elementary textbooks, you see alpha set at either 0.01, 0.05, or 0.10. Those are the three favorites. Typically, the one that is favored the most is alpha equal to 0.05. So let's follow that route. Now, alpha is the probability of committing a type 1 error, that is, rejecting the null hypothesis when it is actually true. Okay, the test statistic, p hat, which is our estimate of the population pull based on our test sample, you have p hat minus, well, if the null hypothesis is true, then p is equal to 0.03, and divided by, and that expression in the denominator is the standard deviation of the population pull. And that's equal to 0.03 p times 0.97 q, or 1 minus p, divided by the sample size. We take the square root of that. Now, since we're testing at the alpha level of 0.05, and it's a one-sided test, that test statistic, which has a standard normal distribution, is going to be greater than or equal to 1.645, okay, if the null hypothesis is true. That is going to be our critical region, okay? If the test statistic exceeds or is equal to 1.645, you have fallen into what's called the critical region, and you will reject the null hypothesis, okay? Now, if you do some algebra, you can find that the values of p hat, okay, the test statistic, the test proportion, is greater than or equal to 0.0356. That's just an alternative way of expressing the critical region. So if p hat is greater than or equal to 0.0356, you're going to reject the null hypothesis. Okay. For p equal to 0.035, in other words, if the alternative hypothesis is that you're generating a 3.5% response rate using the new promotional package, and that's based on our test that we did, what's the corresponding value of beta? All right. Now, beta, by definition, is the probability that you fail to reject the null hypothesis, okay, when the null hypothesis is actually false. Or another way of saying it, 1 minus beta is the probability of rejecting the null hypothesis when the null hypothesis is false. Okay, well, 1 minus beta then is the probability that p hat falls into the critical region, that's equivalent to rejecting the null hypothesis, given if the null hypothesis is false and the alternative is true, and we're representing the alternative by the 3.5% response rate that was generated in our test. Well, then we get this fine-looking equation. That 1 minus beta is equal to, now what I've done is I've taken the previous, let me go back, I've taken that very last line, and I have subtracted 0.035 from both sides and divided by the square root of the standard deviation if the alternative hypothesis is true. That's 0.035 p times 0.965, 1 minus p, divided by the 2,500, which is the sample size. We take the square root of that. Now, that expression in the brackets to the left of the inequality sign, that test statistic has a standard normal distribution, and therefore we're going to represent it by z. We all know and love that from the textbooks. So 1 minus beta is the probability that z is greater than or equal to 0.163, okay, which is what that expression on the right side of the inequality turns out to be equal to if you do the arithmetic. That's the same thing as 1 minus the probability of z being less than 0.163, from which we can infer that beta, okay, the probability of committing a type 2 error, is the probability that z is less than 0.163. That can be looked up in a table of standard normal variates, and that probability is 0.5636. So the alpha level has been controlled at 0.05. The probability of committing a type 1 error, all right, and losing $900,000, there's only a 5% chance there. But the probability of committing a type 2 error and losing $225,000 in profit is 56.4%. Ouch. Not too good. All right. Now, what can we do? What can we do to reduce beta? Because obviously we don't want to live with 56.4%. Well, a couple of observations. First, alpha and beta have, well, I'd call it a seesaw relationship, an inverse relationship. As one increases, the other decreases. Okay? So, if we keep the sample size of 2,500 and we set alpha equal to 0.05, we've already seen, we just worked it out, that beta is equal to 0.56. Now, if I'm willing to give a little bit on the alpha level, I can improve the beta level. So if I move alpha to 0.10, a 10% chance of committing a type 1 error, then the probability of committing a type 2 error reduces to 0.43. If alpha goes up to 0.15, beta reduces to 0.35. If alpha goes to 0.20, beta reduces to 0.28. All right, so you see what's happening. As one increases, the other one decreases. Still not happy with having an alpha level of 0.20 and a beta level of 0.28. So what can I do to help myself? Well, increasing the size of the test sample up front is going to help you out. Now, in this table that appears on the bottom of the screen, I kept alpha equal to 0.05, but I've increased the sample size of my original test. Originally, a sample size of 2,500 would yield a beta of 0.56. If I increase the 2,500 to 3,500, then the beta level will decrease to 0.47. If I go from 3,500 to 4,000, again keeping alpha at 0.05, then the beta level becomes 0.42. All right, well, I can continue, increasing n until I get beta to a size that I can live with. However, since we're all mathematicians here, how large of a sample size would be needed to achieve pre-specified levels of alpha and beta? Here is the formula that you would need to determine the sample size for pre-specified alpha and a pre-specified beta. Just to refresh your memory, Z sub alpha represents the area under the standard normal curve, so that the tail probability is equal to alpha in this case. Now, I didn't think that the derivation of this formula belonged in this presentation, but I have written up the derivation of this formula and put it in the form of a handout. So if anyone is interested in seeing how I came to this formula, I would be glad to send you a copy of the derivation. But getting back to this presentation, suppose we wanted alpha and beta both to be equal to 0.05. Suppose we only want a 5% chance of committing both a type 1 error and a type 2 error. Okay. Well, we replace the alpha by 0.05, we replace the beta by 0.05, and our equation looks like what we have here. Okay? The P0 is the population response rate under the null hypothesis. That's your 0.03. 1 minus that is 0.97. That's under the first radical. Under the second radical, P1 represents the population response rate under the alternative hypothesis, and based on our testing, we found that that's equal to 0.035. 1 minus that is 0.965. If you go to the standard normal tables, or you go to any of the various software that's out there, and go look up the standard normal ordinate corresponding to a alpha level of 0.05, that'll turn out to be 1.645. And since Z of 0.95, Z sub 0.95 is just based on the symmetry of the standard normal distribution, is just creating a left tail probability of 0.05. Those two Z values are just the negative of each other. So Z of 0.05 sub 0.05 is 1.645. Z of 0.95 is equal to minus 1.645. That happens simply because we've let alpha and beta both be equal to 0.05. But if you plug in those values into the formula, you'll find that you need a sample size of 13,593. So let's round it up and say a sample size of 13,600 up front. Okay, that testing that you did up front to determine the efficacy, the pull of the new promotional package, that test sample size should have been 13,600, not 2,500, in order to be able to control both the probabilities of committing a type 1 and type 2 error. Now, that's 5.5 times the size of the original sample. Always the problem of whether or not you can afford to increase the sample size to that level. But that's what would be necessary if you wanted to control both types of error, or the probability of committing both types of error. And as we see from this example, that where the consequences of making an error can be put into dollars and cents, you certainly would want to be able to control both the probability of committing both types of error. And that's it. If you have any questions regarding the presentation, come see me at the Learning Center, or shoot me an email, and I'll be glad to elucidate anything that seems to be mysterious. Again, also, if you're interested in seeing a derivation of this specific formula, let me know and I'll be glad to send you a copy. Thanks very much.